Hi, I'm Ravikran, a PhD student at Human Centered Technology Research Centre at University of Canberra, Australia. Now, I'll be presenting a paper titled Examining Subject-Dependent and Subject-Independent Human Affect Inference from Limited Video Data. Let me give a little background to the question. Automatic emotion inference plays a critical role in building intelligent human-machine interfaces that can understand and respond to human emotions. Emotions are integral to perception, rational decision making, and other cognitive functions. Previously, there have been tremendous efforts to develop methods that can accurately recognize and analyze human affect. Research on emotion inference focuses on either categorizing human emotions into universal emotion classes, namely happiness, fear, surprise, sadness, disgust, contempt, and anger, or mapping them onto a continuous dimensional plane, for example, spanned by the valence or arousal dimensions. Valence is defined as the degree of pleasantness or unpleasantness elicited by a stimulus, while arousal describes the extent of calmness or excitation evoked by it. In this study, we consider the dimensional uh, model for emotion inference, as this model is more representative and can lead to an accurate assessment of the natural affective state. Since emotional expressions evolve dynamically, it is essential to model short and long-range dependencies among expression features which are observed over a given time interval. Affect recognition systems typically use affective data captured in control settings, but recent studies have focused on recognizing in the wild emotion expressions captured under naturalistic settings. The following points are the motivating factors for the problem. Early studies on basic emotions state the existence of a core facial configuration reflecting the emotional states of a person. In contrast, other scientific frameworks posit that expressions of the same emotion vary substantially across individuals and situations. For example, the typical expression of anger might sometimes be accompanied with additional facial movements such as widened mouth, while in other instances, a facial movement might be missing with respect to the prototype. Such variations are considered to be a meaningful part of an emotional expression because facial movements are functionally tied to other factors such as external context and the person's internal affective state. Hence, while inferring affect computationally, it becomes essential to consider models which are both subject-specific and subject-agnostic. Although multiple video databases exist, they are typically limited by the amount of annotated data, unlike affective image databases that contain millions of images. The scarcity of large corpora of affective annotated data can be attributed to A, the difficulty in capturing emotional data under naturalistic condition, or B, the difficulty in assigning static and dynamic emotion labels to large amounts of data. In addition, limited video data presents a challenge as emotional patterns are to be learned spatiotemporally, unlike image data where spatial emotion representations need to be learned. Consequently, how training and test data are divided plays a vital role in determining recognition performance. A comparison of subject-specific versus subject-agnostic settings is therefore critical, especially in lean data settings. We employ both subject-dependent and subject-independent settings to infer valence and arousal scores on the AFWVA and in the wild dataset with limited data. Formally, the subject-independent setting involves the use of training and test sets with mutually exclusive subjects, while training and test samples corresponding to the same subject can occur in the subject-dependent setting. Here are the following research contributions. We examined the subject-independent and dependent settings for valence and arousal inference on the sample-limited AFWVA dataset. All the performance metrics considered here substantially improve in the subject-dependent setting as compared to the subject-independent setting. These results reveal that learning individual encoding is critical for accurate arousal and valence recognition on the considered dataset. We also propose a novel dynamically weighted loss function to simultaneously improve the correlation as well as minimize the error between the target values and predicted valence and arousal values via the CNN LSTM network. To the best of our knowledge, this study serves as an upper limit benchmark for affect inference in the subject-dependent setting on the AFWVA dataset. The following figure gives the overview of the current work. Let me now describe various stages of the experiments, starting with the dataset. To examine emotion inference using limited data, we use a publicly available dataset called AFEWVA, which consists of 600 video sequences with continuous annotations of valence and arousal values in the range of -10 to 10 for each frame in the video sequence. The videos in the database are collected from movies which are closer to real-world scenarios than control lab settings. The 240 subjects in AFEWVA denote the video actors who mimic real-world human behavior. As an initial step, we extract faces from each frame in the AFWVA videos. Given an input video, we employ MTCNN, which is a unified framework for both face and face detection and face alignment. Sometimes face detection algorithms are prone to fail while detecting faces in the wild. In such cases, we employ CLAHE, called the contrast limited adaptive histogram equalization technique to enhance image contrast. The output of CLAHE is passed to MTCNN for face detection. If the face is still not detected, we approximate face based on the face detected on the neighboring frames. We thus ensure that we ensure the inclusion of almost all frames in the AFWVA, which is relatively small to begin with. In each video, we consider a sequence of 8 consecutive frames with a stride of 1 as an input sample. The total number of derived samples from the data set is 25,759, which are then fed to a CNN LSTM network. We use a CNN LSTM network in which spatiotemporal patterns are learned using a 2D CNN network followed by LSTM layers. For the CNN architecture to learn spatial patterns, we chose ResNet 18 network. The final classification layers of ResNet 18 is replaced with a linear layer with 300 neurons, which are then fed to a stacked LSTM layers. This is followed by a linear layer with 128 neurons and a final regression layer for estimating valence or arousal values, which are in the range -1 to 1. Similar to past studies examining dimensional emotion estimation, the performance metrics used here are RMSE, Pearson correlation coefficient, and concordance correlation coefficient. If theta and theta had denoted the ground truth and predicted labels, respectively, the metrics are defined as given in equation 1, 2, and 3. In dimensional effect inference, the aim is to minimize RMSE while simultaneously maximizing the PCC and CCC. The most common approach employed for regression model optimization is to use individual loss functions, namely MSE or inverse CCC, while other studies also use a combination of losses in addition to using the losses individually. Differently, we propose a dynamically weighted loss function defined as L of I equals F of I, the MSE loss, plus G of I into CCC loss, where F of I is alpha times I by n power k and G of I is 1 minus I by n power k, where I denotes the ith epoch in the training phase. Similarly, alpha and k are hyperparameters controlling the normalization and nonlinearity, respectively. Figure illustrates the weight function f and g for a fixed epoch size of 60. For estimating effect, generally, LCCC is used to maximize the correlation between the ground truth and the predicted values. When a combination of loss functions with static coefficients is used, the model tries to simultaneously optimize the metrics, which may result in a suboptimal model. A proposed loss function employs dynamic weights to ensure that the network learns to maximize the correlation initially and then minimize the error. Empirically, the proposed loss function results in improved model performance as shown in the table. To account for optimizing all 3 metrics simultaneously, the proposed loss function is designed to learn the correlations initially and later to minimize MSE in a continuous fashion where the non-linearity factor is controlled by the hyperparameter K. In this study, we perform both subject-dependent and subject-independent experiments for valence and arousal inference using AFWVA. While performing studies while prior studies only performed subject-independent experiments, whether effect inference is required in an subject-independent or dependent setting may depend on the use case. We employ the proposed loss function in our experiments as it results in improved RMSE, PCC, and CCC values as compared to other loss functions. As seen in the table, all performance metrics are improved in the subject-dependent setting as compared to the independent setting. As the subject-independent setting results in lower RMSE and highest PCC and CCC values for both valence and arousal. In contrast, the model is unable to learn generalized features to discern diverse valence or arousal values in the subject-independent framework. To obtain further insights, we use TSNE to visualize the features learned to estimate valence and arousal in the two settings. As can be seen, the learned features for valence and arousal prediction in the subject-dependent setting are better separated as compared to the independent setting, where features corresponding to high or low valence overlap considerably. Overall, the results in the subject-dependent indicate the upper limit for arousal and valence estimation on the AFWVA dataset. Moreover, the results demonstrate that the proposed loss function results in a superior prediction performance. Employing this loss function on the AFWVA dataset, we observe considerably more precise valence and arousal estimation in the dependent setting as compared to the independent setting. Cumulatively, the results reveal that for the small AFWVA dataset with a highly imbalanced distribution of input samples per subject, identity-specific characteristics substantially impact emotional inference. Conversely, emotion-specific representations cannot be efficiently learned across subjects as typified by the poor valence or arousal estimation in the subject-independent setting. In this study, we have examined the influence of limited video data and of an imbalanced distribution of samples per subject on continuous human effect, which is valence and arousal, using the AFWVA dataset. While some studies in psychology state the existence of unique emotional expressions for the basic emotions, on the contrary, others hypothesize that emotional expressions of the same emotion vary substantially across individuals due to the factors such as context, social environment, etc. Hence, to infer effect computationally, it is essential to examine the effect inference using subject-dependent and subject-independent settings. A novel dynamically weighted loss function is proposed and is found to enhance correlation as well as reduce error between the target and predicted values. Empirically, we observe that this loss function results in an improved performance than competing loss functions. Further superior performance in terms of RMSE, PCC, and CCC metrics is observed in the subject-dependent setting as compared to the subject-independent setting. The results indicate that the features of valence and arousal learned by the model are not generalizable across subjects. Visualizations also convey that the features of the subject-independent framework are not as discriminative as the subject-dependent framework. In the future, we plan to explore the influence of individual specific factors on effect inference using other effective video data sets, such as Recola and AFWILE2. We also plan to examine the effect of fusing multiple modalities, such as audio and context, for effect inference using subject-dependent and subject-independent settings. Thank you.